thank you for the kind invitation and for this really nice meeting organized. So I will give a shift of paradigm. I will not talk about charge transfer today. I will just want to show you how molecules has an electrostatic effect. So I will talk mostly about electronic potential, electrochemical potential, and not charge transfer. I will show you current, but the key control of the current would not be the molecules. And my starting point is that the interface is the device, and I show here a standard textbook for a p-n junction. So now I'm going to really fundamentals. So in a p-n junction, we have an interface between a p-doped and an n-doped, and this makes some electrochemical potential change. I connect to the first talk today where they talk about the thermopower. So again, I would talk about the changing the density of states in the two electrodes, and because of this interface that we have here a chemical change, this translates into a strong electric field at the interface, and as a result, there is a change in the energy levels. And this asymmetry in the energy levels is what gives us functionality. So that's the basic of electronics, and we always need this asymmetry, again, as shown in the morning, in the density of state by the temperature gradient. We can also give it by the electrochemical gradient. And I would like to suggest that basically the same idea, I put it here originally in honor of Mark Ratner, that the same idea also was in the basis of their diode. So, but I will not show an isolated diode. I will not show a donor acceptor. But the idea is that a molecule, because of their closed shells, can hold a very strong gradient of electrochemical potential. So I explore this property of molecules, but I will not show anything like a single molecule conductance. So very briefly what we are doing, so we start with a subset. That would be the side view. This is an AFM of a silicon 1110. Silicon is very convenient to work with because it's so smooth. Then we absorb a molecule on it. This is schematically shown. The chemistry that we employ is either radical chain reaction, so by light or heat, we can form a radical on the silicon. So, we start from silicon H terminated silicon, no oxide. Ideally, there is no oxidation at all. And this radical interact with the double bond to form monomer. In a different mechanism, we can also come with activated molecules like hydroxylate and bind directly to the silicon. So these two reaction mechanisms, we exploit them. Then we put a top contact, connect electrically, mostly to DC measurement, and measure the current across this interface. We can also measure occasionally with impedance measurement that give us extra handles, and light to make some kind of a solar cell. So in terms of energy, so again, this is just to show you the dimensions. So here we are nanometric. In the transport direction, we are doing a nanometric change, but we average over a huge area. Normally, most of the results that I will show you were done with mercury drop, which is about 300 micron wide diameter. Now we are using some evaporated lead. We can go down to 3 microns, but it's still very huge, the lateral dimension. And I will show you off mostly these energy diagrams, which is like setting this interface upside down. And the y-axis is the energy, the x-axis is the distance, and this would be the semiconductor with its forbidden energy gap. That's the metal, where the Fermi level is within a field gap, and in between some interfacial modification. And remember, this is really nanometric, it's not to scale, so this interfacial layer is very narrow. And the critical parameter that I would argue that change is this band bending the potential in the silicon. So my working assumption would be that this is the main barrier and not the barrier by the molecules. And I would like to ask what are the controls, what are the chemical handles that we have to change this band bending in the silicon. I hope I won't confuse it too much with I also call it SBH, Schottky barrier height. So I would either use band bending or SBH, but that's the idea. So it's a barrier in the silicon. Due to the short time, I will completely ignore the barrier in the molecule. So what determines the Schottky barrier height? And that was a major debate in silicon or semiconductors, electronics in general. Leading people, there are two major views of it. So the ideal view is by Schottky-Mott, where that's basically an energy balance. So we require that at the interface, both the Fermi level would be equal and the vacuum level would be equal. Because different materials, as I said before, different material has a different chemical potential, this balancing would create a space charge in the semiconductor. And now what I'm arguing that if I add here an interfacial dipole or a strong potential step at the interface, it will change this barrier. So by inserting here a strong dipole, I can alter this balance, and by that I will change the barrier height in the silicon. And there is but the problem was that this was suggested already in 1938, and it didn't work. For decades, the community didn't know what to do with it. So then Bardeen, both Mott and Bardeen are Nobel laureate, Bardeen for the transistor and for superconductivity. The leader people were dealing with this problem. And so Bardeen said that there is a density of interface states here, and the Fermi level would be forced to be at the middle of this density of interface states. And this middle of the level is called CNL, the charge neutrality level. And again, these are still major problems in all organic electronics. There is always a problem how to overcome it. And the problem is that in most important semiconductors, so this is a general relation, so we can combine effectively these two models with a parameter called S. So if S is approaching 1, we will have this model. If S approaching 0, it would be this behavior. And in practice, people found, we didn't really know how to explain it, but in practice, they found that this S factor is close to 0. So this is the dominant behavior for all important semiconductors like silicon, gallium arsenide, and so on. So I think that's my, okay. So this one is, I will call it surface states, okay? Because here there are a lot of surface states. Here that would be the dipole effect. So I will talk about these two mechanisms and how can we play with them. And I would like to argue that there are actually 3 different mechanisms that affect the barrier height in the silicon. Again, that would be the Schottky model with the interface dipole, or the Bardeen model with surface traps. And I would like to show you also this other effect that is someone combining the two intermediate, which is charge injection between the organic layer and the electrodes. And in due of time, I guess I will not have so much time to go into surface traps, but just bear in mind that everything that I talked today, all these 3 components are interrelated. So we cannot, for simplicity, I will separate them, but in practice, they are all active, and we have to make sure that we are really identifying correctly what is the effect that we observe. So I will start with the interface dipole. And this is a bit tricky. So interface dipole is a collective effect. It's not something that we expect to see from a single molecule. It is shown by, not by us, by collaborators, theoreticians. So here in this group by Kronig and Tung, they show that if we have a single dipole, its field line extends toward infinity, the field lines of the dipole creating. However, if we put an array of these dipoles, the field line cancel each other, and outside, so there will be a very strong electric field between the 2 poles, but outside of them, they decay exponentially. Okay, so this effect is really for flat surfaces, much larger, so I don't know, at least 20, 50 dipoles like that. Below that, we are not expecting to see that. And here it's another nice example from a DFT computation from a group of Zoyer, where they use this biphenyl with thiol and cyano, which is supposed to have a very strong dipole across it. However, if it's single molecule, there is a very localized spike in the energy plane. And if they have an array of these molecules, they have a very clear step in the potential energy. So that's the basic idea, and that's what we want to exploit for modeling the barrier in the silicon now. So this is first example where we absorbed a series of alcohols, starting from methanol and up to decanol. This is the chemistry. It is activated by this hydroquinone, but very little hydroquinone remains on the surface. So that's composed most of the monolayer. And here it's a measurement of the work function. So we see that different chain lengths have a different effect on the work function. The methanol decreased the work function considerably. It's 1 electron volt. The gap of the silicon is 1 electron volt. It means that it reduced the work function by the gap of the silicon, and the decanol has the least effect. And now, if the Schottky-Mott model works, I should see the effect of the change in work function on the transport. And that's what is shown here. The top contact was done, so the work function was measured on the free surface. Now I use the mercury drop to contact. This is the mercury drop. The mirror-like is the silicon underneath. And see the behavior. So the C1, the methanol, is the least conducting. The decanol is the most conducting. So it's obviously not a tunneling effect. So in a tunneling effect, we expect That's more or less what we see here, that they start. But in the tunneling effect, we expect the longest molecule to be the strongest insulator. So here we see a complete opposite effect, and we argue that that's for sure an effect of the silicon barrier and not of the tunneling. And now we extract from the value of the current here, we can extract the Schottky barrier, the barrier in the silicon, shown here on the y-axis compared to the modified work function of the silicon after adsorption. And we see this very nice linear correlation. It's negative because, again, that's the Schottky-Mott relation, so it's negative with respect to the work function of the silicon, electron affinity. And so the trend is correct. The slope here is 0.9. And that means that this S factor is approaching unity, which is very surprising for us, because this is the textbook, again, from the 70s. This is kind of well-known knowledge in solid-state electronics. So that's this S factor for very large group of semiconductors. And the notion was that it depends on their ionicity. So oxide-like semiconductor has a very high S factor, while covalent semiconductor like silicon have very low S factor. And what we show here, that actually we could make a junction to silicon with S factor approaching unity, approaching an ideal case. And this has a fundamental importance because it means that this S factor is not an intrinsic property of the silicon, it's related to the surface. So actually surface modification can be very important in controlling the net barrier in the silicon. And now this is a continuation of the same theme, just different molecules. I will go through it briefly because of view of time. So this is a series of styrene-modified molecules. Again, we measure the contact potential difference. We see a nice variation of almost 1 electron volt between, or more than 1 electron, between the methyl termination and the bromine termination. And it's translated to the current voltage characteristic shown here on the semi-log scale. And this is, the inset is linear. And you see that we have an 8 orders of magnitude just by differing the substituent. So it's a huge effect, and the barrier is in the silicon. It's not a direct molecular barrier, but it's induced barrier, and it's a very strong expression of chemistry. So we are very sensitive to the minute chemical changes. Okay, so from this intercept here, I will not dwell into how we extract it, but that's another measure of the barrier at the surface. And the blue line here, so that would be from the methyl. I have a built-in potential of half an electron volt. And I can show that this means that we actually have a p-type. So I started from an n-type silicon. I have such a strong band bending that the Fermi level at the surface is below mid-gap, and that means that I have more holes at the surface than electrons, and that's mean inversion. And I showed in the talk yesterday that it can be actually technologically important for solar cell and creating a p-n junction just by induction and not by changing any high-temperature dopant. So that's a summary. Okay, so with the methyl, we can have something like a very strong gradient. With the bromine, we have something like a conduit. And again, this is just to show that this has actually, I think, engineering capabilities, this modification of the molecules. So I talked about the interface dipole. I want to rush into the charge injection, which I think has a bit larger importance. And the main difference is that the interface dipole is neutral. So the whole effect is within the molecules. It's neutral. Charge injection, the molecules would inject charge into the substrate. And it's important because we can express the dipole effect only if we have a reference electrode. So the dipole effect would work only if I have an interface, a junction, if it's buried between two Fermi levels. The charge injection it can be to any surface. If it's a nanoparticle, or it has much more occasion where it is working. So I will start with our simple alkyl chain. So alkyl chain, they are not donor or acceptor. They're most dummy molecules, and ask what is the region of the dipole that we see. So we know that the alkyl chain reduced the work function. So how can it be? So there are 4 different possible contributions to dipole, and I will walk through them. So the first one is just polarization of the molecule. This effect we expect to see very much if we have the phenyl rings, which are polarizable. That was the principle before with the styrene modification. And we do not expect to have it in the alkyl chain. Another known effect, again, for anyone working in organic electronics, it's called the pushback effect. So any contaminant, any physisorption on the surface will truncate the leakage of, so that's the electron wave function in the solid. There is a little leakage of this wave function outside to the vacuum. So any physisorbed material will truncate this extension. So, and this effect is universally reducing work function. Whatever contaminant in the surface, compared to vacuum, normally the work function would be lower. So this would work. This is a possible explanation of what we see with the alkyl chain. Another possible effect is the bond dipole. So because we make a chemical bond, these are covalently bound, there could be some charge rearrangement between the silicon and the carbon. However, in the specific case of silicon-carbon bond, the carbon has a higher electronegativity than the silicon, so we expect the dipole to be negative on the carbon, and that's work against. So that should increase the work function. So maybe it is there, but it's against the major effect that we see. So I reached to the last effect, that's what I'm calling charge injection, and the idea is that there is some finite charge that moves from the molecule to the electrode, and this effect is still kind of controversial because these are two gap materials. There are no states there. There is not that I have some redox reaction or something like that. The gap of the alkyl chain is 9 electron volt. The gap of the silicon is 1 electron volt. So near the Fermi level, there are no states that can be charged. But still, I would like to argue that there is some charge rearrangement there. And I hang here on a work by Selenak and Breda that they suggested that there would be a fractional charge rearrangement in order to equilibrate the electrochemical potential of the substrate and the organic, the molecule. And remember that this is kind of a virtual property. There are no states. And this would be depend on the hardness of the material. So the softer, more electrons, there would be more larger charge rearrangement. And I would like to give you again an example that we think we see this effect with the alkyl chain. So we absorb exactly the same monolayer, 10 carbon long alkyl chain on different doping of the silicon. So we change the doping of the silicon between highly doped N to highly doped P. And this is the energy diagram what we expected to see. So if now this is the highly doped N, and I change to highly doped P, it shifts the Fermi level downward, and we expected that the work function would be increased by 1 electron volt because now we change the doping. So in this vision, the molecular dipole is constant, and we only change the Fermi level, so we should increase the work function by 1 electron volt. This is the measurement of the work function by UPS, and you see the dotted line is what we expected to see, and that's what we do not see. So the work function is more or less constant. Maybe we have some U shape, but the work function is basically indifferent to the doping of the silicon. So we wanted to understand, and we know very well that our surface has a very little surface state. I showed you before that we could change the barrier height efficiently. So we don't believe that it's because of some Fermi level pinning due to surface states. So the model that we suggest now, again, it's shown here schematically. So if I now will reduce the work function, what changed is actually that the silicon is shifting up. So the dipole on the molecule has changed. I can show it again. So instead of, it's like this is my anchor, and what is changing is the position of the Fermi level of the silicon with respect to the molecule. And now we'll try to show you how we reach this conclusion. So this is a lot of XPS, X-ray photoelectron spectroscopy. This is the silicon core level, and all the core levels in XPS or UPS are relative to the Fermi level of the system. Okay, so if I change the Fermi level, I expect this core level to change. These are the very surface atoms of the silicon. So it's not the bulk of the silicon, it's really the few nanometer close to the surface. And I'm not sure how you can see it. So between highly doped N and highly doped P, I have about 1 electron volt, what we change in the doping. So this is exactly how theory expect. However, for the carbon, this difference mirrors much. So if I'm looking on the levels of the carbon, I see a much smaller difference. And that's why I suggest that there is a charging of the monolayer. I will skip this here. Again, the dotted line is what we expect if the dipole would be constant. So the carbon should not change depending on the doping level of the silicon. However, we can see that this works only for the moderately doped, And for the highly doped N and the, highly doped P and the N, there is a change. So here there is a negative charging of the carbon, and here there is a positive charging of the carbon. And in short, this is a schematic diagram how we see it. So this is the dipole on the highly doped N. It will be the smallest. It would be the largest on the highly doped P because of the charge rearrangement. And in the moderately doped, we'll have some band bending. That's what I show here. But so there would be interplay between the band bending in the semiconductor and the potential drop on the molecules, and the anchor here is the work function of the molecules. So although these are kind of isolated molecules, no free electrons, they do have their own electrochemical potential, and it's forced the energy alignment. So this brings me briefly to the last topic of surface traps. So surface traps are different than this charge rearrangement because their position. So also in the charge rearrangement, I have localized charges at the surface. But surface traps, they are not only localized at the surface, they are also within the forbidden energy gap. And because they are within the forbidden energy gap, they would induce barrier in the silicon. So again, this is a schematic diagram. We have so we believe that if we absorb the molecule, we are able to change the traps and move them because of the chemical binding. We move them outside the gap. I will show here a very short example. That's actually from 2006, when we start working with this monolayer on silicon, and that was our childhood days to learn how to make good monolayers. So you can see this is an oxidized silicon, and you see that as we improve the quality of the monolayer, this is the IV curves are getting more and more rectifying. And we can also correlate it with the very minute amount of oxygen. This is the silicon peak in XPS. So this is a very small peak of oxidized silicon. But this very small peak of oxidized silicon is enough to dominate the current voltage characteristics. So in short, we have to take all these three ingredients in order to design the barrier in the silicon. If we can control efficiently the interface dipole, that would be very important for junction, where we have a reference electrode. Charging injection is when we do not have a reference electrode, like for sensors, for for channels of transistor, if we want to change them, so wherever we do not have a reference. And surface traps are critical whenever we have a lot of facets and a lot of defect area. That's where surface trap would be, passivation of surface trap would be most important. And I wish to thank my colleagues. David Kahn is the head of the lab, and most of the UPS, XPS done by Tatiana Bendikov. And thank you.
With respect to the tunneling phenomena,
yes.
So with more linker length,
shorter molecules was least conducting. Yes.
Yes. So how sure are you when you prepare these surfaces with these alkyl chains? How well packed they are with respect to when I compare C5 to C6, C7?
I mean, our
defects in there.
Basically, if there would be defect, there would be oxidation of the silicon, and then we'll see this high current. If the silicon is oxidized, we have a lot of traps. We cannot get this very nice diode. If I see a very nice diode, it means that I do not have, this is a kind of indirect evidence. We characterize them routinely by ellipsometry, by XPS. So for all these characterization, I'm quite sure that the monolayer is good.
What about IR? IR on looking at the CH stresses?
Yes, so this work specifically, they looked a lot in the IR. Specifically, they wanted to know how much of the hydroquinone is involved, but it's well characterized. That,
okay.
Also, the silicon H absorption is clear in IR, so you can follow that.
So you mentioned this changing of the work function to change the electric field, basically. The dipole.
Rectification in the silicon.
Right, right. So by how much does the work function change, actually?
How much? Yeah, that's something that I forgot to tell. So we see normally, between different molecules, we see about 1 electron volt. It's much harder to It's much easier to reduce the work function. If you want to increase the work function, it's more difficult. There is works with, so we normally do not work with kind of strong donor and acceptor. There are other works, especially Koch in Berlin, so they evaporate these kind of dye molecules on surfaces, and they see even 2 electron volt differences. So yeah.
So that's very large.
This is high, and this works on charge injection. So if you put a strong donor and acceptor, that would be a mechanism of charge injection, not so much dipole, but this is even stronger effect, yes. So
affect the work function quite a bit considerably.
yes.
So this hybridization
yes,
idea.
Yes. There is, I think it was a science publication from Georgia Tech, so they even developed some amine polymer that is a kind of universal reduction of work function. If you put some amine-based polymer, you can reduce the work function of everything. And again, it's a group that's working on organic electronics. That's the motivation.